In this video, we are going to study about wavelength, frequency, and energy of a wave. Let's consider a wave. The upper portion is called a crest and the lower portion is called a trough. The distance between one crest and one trough is the length of the wave, and that's called wavelength and is denoted by the symbol lambda. So this is wave number 1. Let us consider another wave, wave number 2. In wave 2, this is the wavelength lambda. If this is the time axis, then we got one wave in wave number 1 and we got two waves in wave number 2 in the same duration of time. Frequency is the number of waves per unit time. So in this case, the frequency of wave 1 is less than the frequency of wave 2. But the wavelength of wave 1 is greater than the wavelength of wave 2. So wavelength and frequency are inversely proportional. Frequency is given by the symbol nu. Energy of a wave is E equals h nu, where h is Planck's constant. The value of h is 6.626 times 10 to the negative 34 joules second. So if we know frequency, we can calculate energy because we know Planck's constant. The relation between frequency and wavelength is nu equals c over lambda, where c is the speed of the electromagnetic radiation. For the electromagnetic radiation, the speed is 3 times 10 to the power 8 meters per second. So plugging in to the energy value, we get E equals hc over lambda So if we know the wavelength of a wave, we can find out the energy because we know the Planck's constant and we know the speed. Let's do this problem. Calculate the energy of a photon for a wavelength of 100 picometers, which is about 1 atomic diameter. So wavelength of a photon is given by the formula E equals hc over lambda. The value of wavelength is given as 100 picometers. 1 picometer is 10 to the negative 12 meters. Speed of light c is 3 times 10 to the power 8 meters per second, and Planck's constant h equals 6.626 times 10 to the negative 34 joules second. So we can plug in these values into the formula. E equals 6.626 times 10 to the negative 34 joules second times 3 times 10 to the power 8 meters per second over lambda, which is 100 times 10 to the power negative 12 meters get cancelled, second gets cancelled, and if we do the calculation, we get 2 times 10 to the power negative 15 joules. The next problem. Calculate the energy of a photon and the energy per mole of photons for radiation of wavelength 600 nanometer, which is red, 550 nanometers, which is yellow, and 400 nanometers, which is blue. Energy of a photon is given by E equals hc over lambda. So we know the Planck's constant, we know the speed. We have to simply plug in the lambda values. 1 nanometer equals 10 to the negative 9 meters. So for the wavelength 600 nanometer, E equals 6.626 times 10 to the negative 34 joules second times 3 times 10 to the power 8 meters per second divided by 600 times 10 to the negative 9 meters. If we do the calculation, we get energy equals 33.1 times 10 to the negative 20 joules. So this is the energy for one photon. So the energy for 1 mole would be 33.1 times 10 to the minus 20 times 6.023 times 10 to the 23, which is 199 times 10 to the 3 joules per mole, or 199 kilojoules per mole. The energy when the wavelength is 550 nanometer. So E equals hc over lambda, and h is 6.626 times 10 to the negative 34 joules second times C is 3 times 10 to the power 8 meters per second over lambda, which is 550 nanometers, and since 1 nanometer is 10 to the negative 9 meters, 550 nanometers will be multiplied by 10 to the negative 9, This gives us 36.1 times 10 to the negative 20 joules. So this is the energy per photon. For the energy per mole, we have to multiply this by the Avogadro's number. So the energy per mole would be 36.1 times 10 to the negative 20 joules times 6.023 times 10 to the 23, which is 217 kilojoules per mole. Now the next part, when lambda equals 400 nanometers, the energy is hc over lambda, which is 6.626 times 10 to the negative 34 joules second times 3 times 10 to the power 8 meters per second divided by 400 times 10 to the negative 9 meters, which gives us E equals 49.6 times 10 to the negative 20 joules. For 1 mole, this would be 49.6 times 10 to the negative 20 times 6.023 times 23, which is 298 times 10 to the power 3 joules per mole, or 298 kilojoules per mole.